Okay, so I'm going to talk about, oh, thanks. I'm going to talk about stream all things because it's how everything in the world is streams, and also how every problem could be solved with streams, or almost, a lot of them could, and about modern ways of parsing data. You'll see, it'll be cool. I want to start by introducing my co-presenter, Rainbow. Courtesy of Holden, who noticed that I'm speaking without a stuffed animal, which is apparently no longer allowed. So I'm very grateful for that. I'm Gwen Shapira. I'm working for Confluent, which is a company that, well, I'm no longer allowed to say that it's the company behind Apache Kafka because it's all a community, but we do have a suspiciously large number of Apache Kafka committers working for us, working on Apache Kafka and contributing to the project. I do a lot of stuff, so I wrote a nice book on Kafka, so if Kafka is your thing, you should totally read it. Getting reviewed by Jesse, who was here earlier. I'm product manager right now, which is weird because the team no longer accepts my pull requests. They're like, no, 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 you do the PowerPoint, we'll write the code. I used to write code. I used to be a real engineer. And I used to do a lot of consultant. Like if you ask me what's the one thing you did most in your career is go around, talk to companies, help them do stuff with their data, which means that I've seen how data management evolved over the years, and I'm going to talk a lot to that. And then I tweet way more than I should. I even got a book from GOTO Chicago for tweeting so much. and I do, while I'm not supposed to code, I still do. And a lot of the stuff I'll talk about here, I wrote examples for. And you can go to my GitHub account and kind of look up Kafka streams examples, and you'll see a bunch of them. So what happened to data management? Like that's kind of over the course of my career, which started somewhere around year 2000. Yes, I'm old. Until now. So I started as a DBA, and I started as a data warehouse DBA. And data warehouse DBA was kind of a difficult job. And the most difficult part was getting the data model right. If you got it right, everything was supposed to be perfect, but nobody ever got it right. Ingest was a real pain. There was those huge batch jobs, loading data, as they would break every single night, and we always had to scramble to still get the business reports in time, even though those huge batch jobs kept failing. We'd had a lot of techniques about optimizing those nightly load jobs. Like that was like 99% of the work. And then because modeling the data and loading data was so hard, we never caught up with new applications. So some data was always missing, and every single time someone wanted a report, and he couldn't really do everything he wanted to do. Limited throughput was a pretty big issue. Like you could only load that much data in 8 hours window you had every night, and once you tuned the hell out of that, it was like we didn't even know what to do, and obviously nobody even thought that you could do it not in large batches. And then fast forward 2009, 2010, we had Hadoops coming along, like a brand new way to do it. So Hadoop was still batch only, but stuff was a lot better. Now we could skip the whole data modeling, which was totally a pain in the ass, and skip most of the ingest pains. Ingest to Hadoop is easy. You can just dump all the data in there, and someone will figure it out, which as DBA was a huge improvement in life quality. But then I was a Hadoop admin. I helped people set up their Hadoops, and you immediately run into a whole new host of issues, which is that nobody can actually use the data. Like now, the modeling of the data, understanding how to use it and what to do with it, and writing those fantastic MapReduce and later Spark jobs was left for every single engineer in the company. And it turns out that they weren't any better at it than I was as a DBA. It is still just a really difficult problem, and it was still messy. And also, a lot of time, people just couldn't find the data. Like they knew the data is somewhere in Hadoop, but how the hell do we know what it is, where it is, what to do with it? It was just, the pains were still there. They just moved from one team to another, as often happens. And now I'm looking at where the companies that I'm talking to now, and the data lake is still there. People definitely still do this kind of processing. But because of its still batchy nature, people are also moving a lot of the data processing to something that's more real-time, and obviously with much lower latency, but still very scalable, like the Hadoops used to be. And the thing that's scary there is that it's a completely different model. Like streaming and real-time and doing all the data processing live is just pretty new and pretty scary for everyone. I met someone at a very large online cloud service that pretty much probably everyone in the room is using or has used at some point. And he's like, I'm using Google Dataflow. And I'm like, fantastic, how is that working for you? And he's like, well, but I'm using it in batch mode. And I'm like, huh, okay, why are you doing that? And he's like, well, because I'm scared of doing things in streams. And I'm like, I kind of get you. I mean, it is scary, like how to debug it. Like it always goes on. You don't have these 16 hours of day of looking at stuff and fixing things. It's really scary. So I kind of get the whole, yes, streams is scary part, and we are kind of still feeling our ways around it. But it is good to see that companies are doing streams. Not everyone is totally afraid of it. So I'm basically going to talk about the patterns that we discovered. So it's not like silver bullet, this is how you do things, everything works that way. It's like I've talked to all those companies, I've seen what people are doing. Here are the patterns that emerged that seems to be things that people find useful and didn't burn anything yet. And one of the things I noticed throughout this whole transition is that some of not just the way we do things changed, but who does things changed. So as you remember, I started my career as a DBA, but we had the ETL engineers. They used Informaticas and data stages, and then at some point Talend and Pentao and all those, and did drag and drop and build the whole ETL pipeline. And that sort of continued into the data lake. And people like, Informatica for the data lake thingies, I guess. But then at some point it disappeared. And now I pretty much, like when someone is building a modern data pipeline that uses streams, I don't see ETL engineers anywhere anymore. And at first I thought it's just because the job went away, right? Like if you dump all the data into Hadoop, what the hell do you need an ETL engineer for? Which is absolutely correct. But then I looked around and noticed something even scarier. It's all engineers now. Everyone is gone. I can't find, and all the people I used to work with when I started my career, I had those QA people and the people doing data modeling and the sysadmins and the network admins and the storage admins. I used to hate the guts of my storage admin. I think he's working for Amazon now because those are the only people who still hire storage admins in the world. So pretty much everything changed. So I'm not surprised that software engineers are doing those data pipelines and data processing because they're doing everything in the organization. So when you have a software engineer doing the job, it's not just that it's a software engineer who is doing the same things that the ETL engineer did earlier. Like the whole thing changes, like the whole perspective. It's a different person and everything is different. So if you're a software engineer, you're not into let's get data from here to there. You're into I'm building an application. I usually have a business goal in mind. Like that's the thing I need to do. And you're also not really into drag and dropping. Like you're an engineer, right? I know how to write Java or Python or SQL or whatever. I have a debugger. Like what the fuck is those point and clicks, right? So a lot in the space just completely changed. And those patterns that emerged that we are going to look at is, first of all, the fact that we're now streaming everything, right? Like that's the whole transition, that we're doing everything in streams and in real time. It's about how do we keep compatibility. That's a problem that kind of kept popping up starting from the keynote yesterday. Like Martin Followers mentioned that compatibility is a big issue when you are building applications that move data around, and it's still a big deal. And I'm going to talk about how to, some processing is just ridiculously simple, and now we can do it at huge scale. I'm going to talk a bit about that. And then also how to solve the really interesting problem of doing streaming data enrichment. And everything is going to go through an example of, it's kind of a merge of two customers I worked with in the last few years. And they're both large hotel chains, each doing its thing slightly differently, but a lot of things are in common because it's the same problem domain. And then, I don't know, like Hyatt is here in Chicago, but those are actually competitors, they're not the same thing. But I hope it will look familiar. So let's start with something that, when I wrote the slide, I thought it's a bold claim, that all the data is event streams. I didn't expect that the Starting from the keynote and every single presentation afterwards, we'll also repeat everything is event streams. And by everything, I mean that, OK, you're the hotel chain, and you have the website, right? And people look at pages, and you want to know what people are looking at. Definitely events, right? So you can capture those events. And people look at specific rooms. Those are definitely events. And people have emails, and they click on links to see your promotions. Those are events. Searches on the website are events. Someone booked a room. It's an event. When you get to, if someone is a loyal customer and he changes his email address on your database, an event. If a hotel is under maintenance, it's an event. If you get to the hotel and check in, it's an event. If you go to your room and open the door, you know how you do it? I bet that's an event too. If you go into the minibar and take out a beer, it has to be an event. Otherwise, how in the world will they bill you? So how much internet do you use in your room? It's an event. It's a bunch of events. They have to measure it. Otherwise, they can't really do any kind of capacity planning, et cetera. Everything is measured. Everything is tracked. That's the kind of world we're in today. I bet that they also collect information from your phones through the Wi-Fi somehow. But I don't want to dig into that. So I hope I convinced you everything that happens in your database is an event because you can do a change data capture in the database. Everything with a sensor, everything in a log, everything in an application, all events. And we look at one of them. We'll start by looking at one of them, which is the page view event. Pretty much every company in the world has a website. Everyone cares about what do people do. Everyone cares about page views. And if you look inside the page view event, you kind of get something that's pretty similar, right? You have like a session identifier, usually from the cookies, to kind of track how the person moved around. You have a timestamp, because everything in the world should have a timestamp. You have kind of what they're viewing right now. He's viewing a property. Since he's viewing property, we also have the property ID, so we'll know what he's looking at. And because he's logged into our website, we also have his loyalty ID number, so we actually have a lot more information. We offer rewards and things, so we will get all this extra information associated. That's super important if you're a hotel. And then we know that he's on a website because he clicked on a link from a promotion that we sent him by email, and tons and tons of those metadatas. What do we do with those events? Well, a lot of services are interested in them, right? That's the event-driven microservices architecture. That's what it's all about. You have a lot of people interested in those events. You want to have a feature on the website that says people who looked at this room also looked on those 5 other slightly more expensive rooms. Maybe you're interested in those. Or 20 other people are also looking in this room. Please book it fast because who knows how long it will last, right? You want to do A/B tests. You want to know that people who search for this ended up booking the other thing. You want to know how relevant your search results are. If your email promotion is actually working. Affiliate programs. These days, you know how someone may blog about their fantastic vacation, and you'll have a bunch of links to the place they stayed at. And if you click on the link, the blogger, and you actually book, the blogger will get paid. That's very important to track page view events just for that kind of system. Never believe anything written in blogs. That's definitely not mine. But yeah, that's it always scares me how much of the ongoing lifestyle blogging ends up being marketing. So we have all those events, and we have all those services who wants to get these events. And if you kind of naively, every time you have someone generating data and you have someone who wants the data, have them talk to each other, kind of HTTP request response kind of thing, that gets really messy, really hard to operationalize. I usually dig a lot into it, but I feel like this entire event was all about how hard it is to debug, troubleshoot, operationalize a bunch of events who talk to each other with ephemeral messages that nobody can really track. So pattern number 1, the way I really like doing it, is basically publish everything into Kafka. And Kafka was written originally as kind of a publish, subscribe message bus on steroids, just open source and meant to scale really, really, really well, which is why companies like LinkedIn can actually afford to publish everything into Kafka, because it is the only thing that's capable of scaling. They tried ActiveMQ earlier, and that didn't end up very well. And then you have all those subscribers who can read from Kafka. The other cool property of Kafka is that it scales really well with a high number of subscribers. That's another thing that MQs tend to not do that amazingly. And it also scales with different type of subscribers. So if you have batch subscribers that just read stuff every hour or every day, Kafka will actually handle them pretty well, as opposed to message queues that has to keep state in memory for all those subscribers. That's why we can get data to Hadoop and to the data warehouse as well as to stuff that's more real time. So that's kind of the idea. If we look slightly inside Kafka, we can see why it's a good idea. So the basic unit of information in Kafka is the log. If you haven't read, my CEO wrote a really nice book called I Love Logs. And before that, there was a really nice O'Reilly blog post, everything a software developer has to know about logs. And he talks about logs as an abstraction. Because really logs is at the basis of everything, right? It's not just your application logs where you write, oh, this happened, oh, exception. It's also, if you are a database, every database in the world, every NoSQL, SQL, whatever, they have the write-ahead log, right? They keep writing everything that happens, every single update, insert, delete, commit, rollback, everything goes into this log. Everything in the world is a log of events, so Kafka is a very good abstraction that allows you to model pretty much everything that's going on in your organization. So the way this log works is that we have this sequence of events, and you keep writing, and every time you write, it comes to the end, and Kafka's guarantee is that it preserves the order of writing across this one log. And then you have readers, and the way it scales is that each reader basically remembers that I am now at message 5, which means that I read message 0 to 4, and now I'm at message 6, and now I'm at message 7. So Kafka doesn't have to keep track of those messages were acknowledged, but those messages weren't, which is most of the load on a traditional MQ thingy. So this is pretty useful. It's fast, it scales, it's easy to understand, which is important. As someone who debugs Kafka, easy to understand is important. I like simple. But obviously, one log can only fit on one disk, maybe, if we try to keep the whole sequential thing. And we actually wanted to scale. So the way Kafka works is that it has topics, and topics have partitions, and each partition is a log. So you scale by saying, OK, all the page view events go to this one topic, and this one topic has 100, 1,000, whatever partitions. And then we have maybe 10 brokers. Each broker gets 10 partitions, and that's how things are kind of load balanced and distributed and so on. Order is still maintained in each partition. So you kind of have to make sure that all the events that are relevant together, for example, all the page views from one session, all the page views from one user, they go to the same log, so you can process them with the same reader. And the way we do it is basically we have keys, and we use them as partition keys. So that's pretty straightforward, like the way most systems would work. So back to our page view and all those consumers. We now know that we have Kafka, page view events go into Kafka. All those things are consumers reading data from Kafka and processing it. And this is kind of the way it usually looks. You have those events going into Kafka, and then you have all those services. So maybe someone is getting the events into a database. He does create table. We have the timestamp. It's a number. Fantastic. You can see the timestamp is indeed a log. Number of seconds, 1970, the usual. You have a search something. It needs to parse the date. No worries. New date. Give it a timestamp. Everything is fantastic. That's how it works. And then one day, a developer says that, hey, number of seconds since 1970 is horrible to debug. It's unreadable. We need an easier format. Let's go with something more readable. And he makes the change. And immediately, everything across the organization breaks. That's the way life is. Yeah, it's really sad. I know. I'm sorry. So, and that's, you can think I'm making this specific example with the timestamp format up. But I've actually seen it in one of my bigger customers, how this small change blows up everything. And they ended up having to reprocess something like 4 terabytes of data to overcome the problem. Then I think that, OK, my customer is uniquely crazy. But I've been at a Strata talk by Uber, and they talked about the exact same problem. So it's not just that my customer is crazy. This actually happens to people who are supposed to be really good engineers. So yeah, I guess if it happened to you, don't feel ashamed. It's a thing. But we still need to prevent it from happening. So which brings us to pattern number 2, the fact that we need to somehow maintain compatibility. Right? You write an event. You need to make sure that people are capable of actually reading it after you wrote it. And that's something I feel very strongly about, because all this conference, I heard people talk about compatibility. And they talked about compatibility in terms of services talking to each other. But if we accept the premise that services talking to each other via REST API is actually not that good of a way to scale and not that good of a way to process data. And then compatibility at that level is not what you should be worried about. You should worry about it, but that's not the big thing. The big thing is that if you're doing event processing or stream processing, the messages in the log are the schema, right? They're the schema, and they are the API between the different services, right? That's the contract. You produce an event, it has a certain schema to it, it has a certain types. Everyone has to read it. The contract is what the event contains. So it's super, super important to maintain. This is your API. This is the thing you need to control compatibility for. And it's even worse than just those APIs with messages because those events can stick around for very long. So if you decide to save data for a month in Kafka, or 3 months, or 3 years, which has been known to happen, you're now committed to allowing people to read data with the schema that you've used 3 years ago. So that's pretty crazy. And we need to at least know when we did bad things. And one of the important things about compatibility is that people tend to miss is that you need to do it as early as possible. Like, a lot of people talk about keeping compatibility in production and having safeguards around production and not allowing stuff that breaks to write events in production, which is great. But even if you deploy to production 3 times a day, it's probably fine. But not all organizations deploy data 3 times a day. Some of them deploy data once a month, for example, like changes. So you really want to hopefully be able to catch schema changes when someone makes the first commit to his branch. Or if it's not on the first commit to his branch, maybe when you do a merge. And if it's not when you do a merge, well, you do have nightly tests running via something like Jenkins, right? So that would be a good time to verify that schemas are still compatible. And if you don't even do that, maybe you have a staging environment. That would also be a really nice time to check that schemas are compatible. One of those, don't wait until production because that's kind of like last resort kind of thing. Like if you have to roll back a change from production, that's kind of ugly. So you kind of want to integrate with all those wonderful development tools we all have, Git plugins and Maven plugins and Jenkins plugins and all those things. Make sure you check compatibility there. So Confluent has an open source schema registry, and we have Maven plugins, and we also have the things that keeps it safe in production, which can also be used in test and staging, et cetera. I usually don't recommend actually running these kind of schemas and compatibility checks on the development environment itself, because usually when you just develop in your own environment, you want to be able to iterate and test a bunch of things. Worrying about it at the stage of after the first commit or nightly test seems like a reasonable compromise for me. Anyway, you don't have to use Confluent schema registry, but do some things that keep things compatible. That's the key point here. Third pattern, having ridiculously simple, sometimes you just have to want to do really simple changes to messages. So for example, you happen to have the credit card transaction. This is completely kind of made up, right? You wouldn't really have in a page view event a credit card number. But suppose you did and you wanted to mask it. Just imagine this is not a page view. This is pretty simple, right? You read an event, you change one field, you write an event back kind of thing. This is really simple. So there could be a bunch of ways to do it. The easiest is basically to run a Kafka consumer. And it's just, Kafka consumer is basically an API that you do subscribe to a topic, poll, you get an array of events, you iterate, you make the changes, and now you need to also do a produce or do something with the data that you just got to make sure that the credit card is gone. But it's very straightforward. And the thing that makes it very, very ridiculously scalable is that you can basically write one Kafka consumer, and if you just deploy one of them and say read data from the page view topic, it will just read from all the partitions in the topic. But what if you have 1,000 partitions and millions of events per second, and this one poor consumer can't handle it all? Well, you just start another one. And they magically, and by magically I mean through a complex Kafka protocol, will talk to each other and figure out that, hey, I'm doing those 3 partitions, you're doing the other 997 partitions. No, they try to do it 50-50. You say, oh, it still doesn't scale, you start another one. OK, I'm doing these partitions, you're doing the other partitions. And this goes on until you have one consumer per partition. You can't have two consumers per partition because then we don't guarantee order and any of that. But and so that's why I kind of like have a lot of partitions. But until you exhausted that part, then it scales really, really well. And as you can see, you can do consume from a topic, do stuff, produce to a topic. It scales really well. This would be the hipster stream processing pattern. And the reason we call it a hipster stream processing is that over in San Francisco land, where we don't drink Bud Light with lime, we have those hipster people, and they ride fixies, which are bikes not just without gears, but without a free wheel. You just have to keep pedaling. They have no brakes. It's really, really, really weird. It is. And the things that they love about those bikes is that they're super simple, which is true. And that's the thing that I like about hipster stream processing, is that you just have a consumer and a producer, very small app, it scales well, super simple. I love simplicity. And this works great until you hit the first big hill. In San Francisco, you hit the first big hill really, really soon. And that's where simplicity no longer works, right? Like, you don't want a fixie on a large hill. Well, no matter if it goes up or down, you're dead. And that's pretty much, so what are the hills when stream processing? The hills are things that are stateful. Things that are stateful would be either joins, which are kind of hard. They would be aggregates, like window aggregates. You need to maintain a state. If you crash, you still need to somehow restore the state and figure out what to do with it. That's really hard. And the other thing that's kind of hard and people don't think about it is that dynamic configuration is really hard in a distributed system because you have all those consumers, and now you want to change a config somehow, and you need them to all basically start together. You don't, unless you especially built for it, half and half is really difficult. So dynamic config changes is another hard problem. So kind of like, so hipster stream processing scales really well for simple problems, not so much for harder problems. And then there is also, like, what do we do if there is a data store involved? Like, we actually, I'll show later why, but you happen to need to get some data from a database or to get data to Elastic. Can we do it in a simpler? And the answer is that there is Kafka Connect that exists to make it even simpler. And the reason it's awesome and so simple is that you don't have to write anything, basically. There's just like, we have like 50 plus connectors already out there. So, of course, the easiest to write software, the fastest with the least bugs is the one you never had to write yourself. So that's not a bad option at all. Like, there's a lot of data system out there, but I'm betting with something like 80% certainty that you have MySQL or Postgres or Oracle or Cassandra or MongoDB or Elastic. Like, one of those 6 you probably have somewhere around. So it's like the 80-20 rule, and we have 50 connectors. So one of those you'll probably have around. And how does it work? Why do I claim that it massively scales? Well, it kind of runs on its own worker nodes, which can be Docker containers or whatever. And it has a REST API. So you install a bunch of those nodes, and you have a REST API, and you can say, hey, please get me data from a log and from an MQTT, this kind of an IoT thing service. And it goes to the respective data stores and say, hey, it doesn't say give me the data yet, because that wouldn't scale, right? I only have one of each. It says, how much data do you have for me? How many indexes, how many logs, how many files, how much data? And then it looks at the data and says, so I need to have that many tasks. And you kind of configure how many tasks you can have maximum. But the idea is that you'll have like a task per CPU, so each one is one thread, single thread, and now it's all parallelized. And you didn't have to do any of it, but it's fully parallelized. And another nice benefit, because of our magic coordination protocol, if that one dies, the task will magically move its way to an available worker. So that's very convenient. And by the way, 90% of the time working on the presentation was the animation. I fucking hate PowerPoint. Kafka is easy. Kafka Streams is super easy. PowerPoint is hard. So that's kind of cool. But OK, so now we have data from databases. We have those simple processing. We got rid of credit card numbers. Now our hotel has a new business case. We want to do a promotion. We have platinum members. And we have a new beachside property in Hawaii that we want to promote. And we decide that if a Platinum member looks at any kind of beach property anywhere in the world, we will send him an email about the awesome deals he can get in Hawaii because we want him to book hotel in Hawaii. OK, fair enough. That's pretty normal. A lot of hotels do it all the time. And this means that we take a page view event that have session and timestamp and loyalty ID and property ID. But what we really need to know is things like, is it Platinum? Is it a beach property? Like, we need an enriched event. We need more. Our service that has to decide has to get more information. So our architecture, excuse my drawing, ends up being a bit like that. You have those events going into Kafka. You have your still super simple consumers that gets them. But then you need to enrich the event. And then you need to pass it on to decide whether or not it's a promotion. Suppose that you also write your decision to Elastic so data scientists can do A/B testing and make decisions. And then you have a producer sending an email to the a message, an event to a notification service saying, please notify the user, send an email, etc. So you kind of have this pass-through thingy. And now the only question is, how do I write the enrichment service? How do I have this event and I need an event with more data. So our first attempt is to say, well, we have a database with all the information. Let's go and get information from the database. Or if you're really, really nice, you say, oh, we have a service that provides those APIs that give us information. Let's go and talk to the service and have him talk to the database and give us all the information, which is slightly better, but not that much, because we still have a pretty big issue. And the biggest issue is latency. That just takes time. The second biggest issue is throughput. Like, just because Kafka scales to gazillion events per second doesn't mean that every service in your organization is going to scale the same thing. So you have a huge fire hose trying to go into a pipe that big. Especially important if you go directly to a database. Databases can scale 10,000 events per second, like, without killing production accidentally. Like, your DBAs will kill you if you try to do 100,000 or a million of them per second. Kafka can do a lot more. So you have to be very careful not to DDoS your own database accidentally. Of course, if you're using Amazon something, just go to town. You pay for all of the events. They will love you. The other problem is availability. Like, if you just talk to one service, no big deal. One of my customers needs to enrich each event. He needs to talk to 11 different services. And I heard that's not even the worst thing he has to do. So if you have 11 different services, one of them will have an issue at any given time. Like, 90% probability, one of them will have an issue. What do we do now? Like, I have an event. I have to enrich it. Like, OK, so I have to keep retrying, and I have to manage all the retries. It's a pain. We can do better than that, guys. We can do a lot better than that. Enter the streams table join. One side, we have a table with the state of all our members and what is their account status. And on the other side, we have a stream of events with IDs that we somehow need to join both of them. And the way we want it to end up is that we have a local copy of database. That's a pattern that everyone in this conference kept talking about, right? You have a local, read-only, in-memory cache of the data that your application needs. And the way we create and maintain, obviously, caches has the problem of getting stale. And we don't want it to get stale. We want it to stay alive and active. So we add another consumer. His entire job is to get the events about all those updates to the table from Kafka and keep on maintaining this cache. Fair enough, but how does those events from the database even end up in Kafka in the first place? That's called change data capture. You take stuff out of a database, and basically you read a commit log, update, insert, delete, delete, and you turn it into a log of events. Basically, turn a state into a log. That's a super, super important pattern. Kafka Connect has a bunch of connectors specifically for that. Or if you're into Oracle, you have Golden Gate, you have Attunity. There's a lot of ways to do change data capture. Super well-known pattern from the ETL days. So we used all those things to take a state in the database into a stream of events in Kafka, and then we turn it back into a state in the application. So we kind of do this back and forth, pretty much what it looks like. We take the state, turn it to a stream, back into a state. Of course, now that you have a stream of events, you can also do a lot of stuff you couldn't do before, right? Because now you have the entire history of your database at your fingertips. You can see how many people book properties and then immediately cancel them. You couldn't before because the database only has a specific state at any given time. So you can do a lot of cool stuff with that. Am I completely running out of time?
No, you're good.
I'm good. Cool. OK. OK, so this is one of the things that is, it kind of sounds good when I'm waving my hands all over. But it turns out that doing a stream-to-table join in reality is not always trivial. Like just you have to maintain this table in one thread, and you have to have those things coordinate. And then you have this cache. If you fail over, you have to recreate it from the stream. If you want to be fast about it, you need to somehow maintain snapshots, which is kind of its own kind of challenge. So there's a lot of stuff that you have to worry about if you implement it. Like it's always like, it's all fun and games until you have to think about what happens if something crashes. And then you find out that it's actually an hour downtime until we manage to recreate the state from this stream of events, and nobody wants that. So, oh, we actually need an in-memory database. Oh, the in-memory database has to persist. So we use the RocksDB to persist it. And then we have to say, OK, but if this crashes and starts on another machine, what do we do? Like, is there a way to make it stateful in Kubernetes? We're still, by the way, anyone knows if there's a way to have stateful containers in Kubernetes? Because, yeah, I'll find out before next time I'm doing this presentation. So Kafka Streams tries to make it easier by hiding a lot of the, oh, we have a local RocksDB instance, and we take snapshots, and we try to make recovery faster. We just give you a very nice API. Basically, it's called K-table. We're saying this is a stream that represents a table. And then we say, OK, do a left join. And the example is on our website. And you can kind of take a look. And there is a blog that just explains how it works in either delicious or excruciating detail, depending on how much you like details. Whew. OK. So I have bonus content on how to join streams to each other, which is kind of cool. But I can also take questions in the remaining 10 minutes or so. Anyone has preferences? Like if you were burning with questions, I'll go to questions. Or if you're not, then I can just keep on talking. Anyone who really, really, OK, question. Sorry? Oh, you want the bonus content. OK, anyone has burning questions that he feels he will not sleep if I don't answer. OK, we're good. Bonus content. So we have another app. We want to decide on search relevance. The way search works is that the user searches for hotels in Philadelphia. And what we really want him to have most of the people just click on the first result and book it, and then maybe a few more on the second result, and the rest kind of in the first page. We don't really want anyone to keep looking, because that means that our search absolutely sucks. In reality, well, how do we even know, right? Like, we need to somehow measure what do people click on when they search. So now we have two events. We have page view events, which are the usual page views. And we have search events, which is what people search for. Session, timestamp, user ID if we have it, and the search term. So now we know what people searched on the search term, and we know how often they search for, and we know what people viewed. But we need to somehow put it together, right? Like we have those two streams of events that we need to get together. We really want to say that this search caused this click, right? So it's a kind of, we're trying to infer a casual relationship. Obviously, it's just inference, but a good inference would be that if the click comes within, let's say, 20, 30 seconds of the search by the same user, then it's a match. And yes, he searched and then clicked. If the click comes half an hour later, it's probably he searched through Google and somehow found something in another way, maybe Expedia or something. So we have this kind of inference, which means that we have to do a join on two things, right? The first is the session ID, to make sure that we're actually looking at the same user. And the second is time. We need to do a join based on time, right? We have this 10-second window in which stuff still counts. I say I was slightly optimistic. This is a 5-minute window. But we basically, what we do is now we have two caches. One cache looks at 5-minute window of one stream. The other cache keeps 5-minute window of the other stream. And we basically keep updating those two caches and trying to join them. So we have kind of a hash table with events from both that we keep matching and also keep aging stuff out, which is a very nice example of how the kind of data structures that you really hate in job interviews end up being really, really useful in the real world. Like if someone asks you to maintain a hash table that allows you to do hash joins and also allows you to expire events as they get older, you'd probably say those crazy interviewers, nobody would ever need it in real life. And here we are. And as time goes by, you keep just maintaining those hash windows and keep joining and keep emitting results of the join. Fairly easy. The only question is that time is obviously really, really critical here. If everyone has been in the beam, I'm sure you've heard it before. But time is really, really critical. And there's a lot of ideas of what time is it that exists in a streaming system. It can be the times that the user actually clicked something in his browser, like the user really did something, or the web app got the click and loaded the page and created an event, or the producer in the web app created an event to send into Kafka. That's slightly later than when the web app first created the event, probably, when the producer actually did the send. We may be doing some batching. And then there's the times that the event really got to Kafka, which can be a long time later. Who knows what network partitions exist. And then it can be the times that the stream processing app is reading the event, which can be months or years later for that matter, because who knows when we decided to add this kind of application. So we need to be a bit careful about it. The best time is obviously the ones that your application put in. In lieu of that, Kafka producers always put in a timestamp just in case. And if you have an old producer that doesn't do it, Kafka itself will put in a timestamp also just in case. So you have a lot of places. Just don't do the whole, if now it's 9:30 and my web application and my streams application just got the event, then the event is at 9:30. This is pretty much never ever correct. Don't. Okay, and then if due to network partitions you gotten late events, our system is actually capable of joining to an earlier hash table as long as we actually keep them in memory. So you can even say something like, please keep all the hash tables live in memory, especially if they're small enough, for maybe half an hour, because some of our applications end up reporting stuff a bit later. So that's a nice thing that you can do, right? You can just basically take an event, say, oh, it's old, let's join it with an older hash table. It sounds super complicated, and it is actually very challenging to implement. Ask me how I know. So you need those two buffers, and then again, you're maintaining state, failover, all those things that make life fun. Again, Kafka Streams makes it easy. By the way, I'm saying that Kafka Streams makes it easy because I know Kafka Streams really well, and I wrote all my examples in Kafka Streams. I'm not saying that, oh, it's really hard in Flink, or oh, it's really hard in Spark, or oh, it's really hard in Beam, because I wouldn't know. I don't know Flink, I don't know OS. I know Spark from like 3 years ago. We definitely didn't have it then, but who knows what they have now. Nope, I guess nope. Flink may have it. They are slightly more streams forward. Maybe Google Dataflow probably has it because they keep talking about it, so I'm guessing they have it. So this is an example. Don't take it as we have it and they don't kind of thing. We love all stream processing systems. That's kind of the thing with Kafka, right? Because we work with everyone. And then we can, you can see an example of how I do it in my GitHub. By the way, Kafka Streams is still at the point where APIs sometimes change. So at the time when you look at the examples, there is some chance it wouldn't actually work. Pull requests are really, really welcome. It's just small API changes. OK, going back, stream all things into Kafka. Keep compatibility. If you listen to nothing else from this presentation, please keep compatibility. Nothing else will screw you over as hard as breaking compatibility in events. Use whatever you can to make simple stuff simple. And then if you need to do complex stuff, then there is these nice enrichment patterns. Please don't write stream processing applications that have to query 11 services. This will bite you slightly less hard than compatibility, but not zero pain. If you like this kind of stuff, we are doing Kafka Summit. And it's in New York, which is kind of close by if you're in Chicago. And you have this nice discount, and it's next week. So it's kind of last minute if you didn't register yet. But it's going to be a lot of fun. And Dean said he's going to be there, by the way. So he's a totally good person to meet, even if you happen to be in New York City.
Or save some money and meet me back.
Yeah, so I'm done. I know it was fast. Do we have time left for questions?
Yeah, a few minutes. So earlier there was talk, I had mentioned it as well, of the idea of all of these streaming engines supporting Beam as like a top-level API. Has there been any discussion about that in the Kafka streams case?
I think we've gotten questions, but we got questions about a lot of things. Like we get questions about when will we support Scala, and when will we support Python, and when will we support Go, and when will we support .NET, and when we support Node.js. So we have a lot of, like, just prioritizing the whole thing is really hard. So right now we don't. Obviously, in the open source community, the easiest way to highly prioritize your request is to have someone go ahead and just contribute a nice bunch of code to the project. So that's a way to get it higher. So I know that for Python, a bunch of people kept asking, and we kept like, well, we'll get to it, but we're not really there yet. And then they just went and opened the GitHub project Kafka Streams Python, where they're doing their stuff. So I'm guessing that at some point, if enough people are interested, there will be a Kafka Streams Beam kind of showing up, probably in Beam, right? Because they host most of the integrations, right? They don't really put it in the other project. Like I think they host the Spark streaming one and so on. So yeah, I'm guessing one day either we will get there first or someone else will get it there first. But yeah, I'm guessing that it will happen. I'm very excited about the idea that, again, I'm an ex-DBA. I wrote a lot of SQL. And I moved from Oracle to SQL Server to MySQL. Basically, almost no hitch, except how the hell do I take backups? Because a lot of my scripts in SQL still worked. And I kind of expect Beam to end up, I hope it will end up doing the same thing for us. Yes?
Is there an off-the-shelf feature that I can review things in Kafka Stream, or do I have to run Apache?
Oh, that's an excellent question, because earlier this week, the idempotent producer has been merged into Apache Kafka, which means that you can actually avoid duplicates in Kafka itself. You can have producers that basically checks for lack of duplicates, and it does sequence numbers. It does pretty complex stuff before it writes data to Kafka. So we think, and then Streams itself is using those commits and checkpoints to make sure that it's exactly once. So we think that we reduced drastically the need for the duping. At least we hope so. The other cool thing about the idempotent producer is that we added transactions. So you can now write to a lot of different topics and partitions. And you say begin transaction, write, commit. And you can have read committed consumers that only read the stuff that was committed. And if something got aborted, they will not see partial transactions, which is absolutely mind-breakingly changes everything in my world kind of thing. And I'm super excited about it. Kafka Summit, the one we almost missed, we will have a talk about exactly how it's done and how to use it and all the gotchas, which apparently there are gotchas. The biggest one, people keep asking me, is it slower if I use transactions? Because everyone knows transactions are slower. It's actually significantly faster, not because transactions are faster. We didn't break physics or anything. But while we implemented transactions, we also optimized the data protocol of Kafka by a lot. So basically, if you produce more than 2 events every 3 milliseconds or something, you're saving, you're sending a lot smaller batches. Even if you don't compress anything, it will just send you smaller batches. And that magically makes everything faster, because apparently it's always the network that is the bottleneck. Or it's either network or disk. You save either way. I'm here tonight and then flying out really early. I have Twitter, Gwen Shap, if anyone feels like chatting about data integration stuff. I'm very much into it.